Good morning from Orbital ATK's test complex at Promontory, Utah. Today, a team of NASA and Orbital ATK engineers are getting ready for the first qualification test of the 5-segment booster that will power NASA's Space Launch System and Orion spacecraft on future missions to deep space destinations. I'm NASA Public Affairs Officer Stephanie Shearholtz, and I'm here today outside the Orbital ATK Test Engineering Support Center. Today's test is a major milestone for the agency and the Space Launch System program as we continue on our journey to Mars. This 2-minute test will generate 3.6 million pounds of thrust. The test is set for 9:38 a.m. Mountain Time, 11:30 a.m. Eastern, and the countdown is progressing normally. We'll have full coverage of today's test for the next hour as we progress through the countdown, the test, and reaction afterward from managers. You can follow along on social media with @NASA and @NASA_SLS on Twitter, NASA SLS on Facebook, and the hashtags SLS Fired Up and Journey to Mars. SLS will be the most powerful rocket ever built and will send astronauts in the Orion spacecraft far into the solar system. It will also have the ability to send other payloads, like scientific robotic spacecraft, to places we've never explored before. While engineers have been preparing for this booster test and making progress in all areas of SLS development, NASA's other exploration systems programs also have been making progress of their own. In December, NASA's Orion spacecraft successfully flew in space for the first time and returned home after traveling to an altitude of about 3,604 miles, farther than a spacecraft designed for humans has been in more than 40 years. At Kennedy Space Center in Florida, where SLS and Orion will begin their deep space journeys, the Ground Systems Development and Operations team is transforming it into a multi-user spaceport. They just completed testing of new traction roller bearings on Crawler Transporter 2, which is being upgraded to support up to 18 million pounds to transport the Orion and SLS to the launch pad. Several years' worth of work and preparation have led up to today's booster test. To learn more about the booster, we'll go to Bill Hubscher, one of our media specialist support staff from NASA's Marshall Space Flight Center in Huntsville, Alabama, where the SLS program is managed.
Good morning, Stephanie. I'm outside of the viewing area, about 1.5 miles from the test stand, as well as a few hundred folks are out here viewing it with me, waiting for the smoke and fire to usher in the next chapter in developing this amazing vehicle. And I'm joined by Bruce Tiller. He is NASA's Deputy SLS Booster Program Manager. Bruce, thanks very much for taking the time with us today. First of all, tell us a little bit more about this particular booster. How long have you and your team been designing this for SLS?
Many years, Bill. We actually have fired 3 development motors already, so we've got a lot of experience with this design. You could almost say we've been working on this thing since the shuttle program, because many of the pieces that are on this booster actually flew on shuttle. In fact, someone told me the other day that the aft skirt that's on this motor was actually on STS-1.
Wow.
So we're taking advantage of what we had during the shuttle days, and we've added to it and improved it to get some more performance that the new vehicle needs. And so it's been quite a while. So we're getting to that qualification phase, and this is exciting because now this is for score. So we've done some development, and now we're really gonna qualify our design for the vehicle and get the performance they're looking for.
Well, for the folks at home, as well as a little bit of clarification for myself, a lot of people will sometimes call this a solid rocket motor versus a solid rocket booster. Can you tell us the difference between the two terms? They're not quite interchangeable.
You're right, and I can. So the motor is what we're testing today, but there are parts of the booster on a motor test as well. The booster includes both the top and the bottom, so to speak. The motor is the part in the middle that actually produces the thrust. It contains all the propellant, and it's the pressure vessel that actually expels the gas that gives you the thrust, and it goes out the nozzle. The booster includes all of that and more. It includes the nose cap and the avionics and the forward skirt. the aft skirt and the thrust vector control system is part of the booster as well. And of course, then you add the parts that attach you to the main vehicle. So the booster is everything that goes on the SLS vehicle. The motor is I guess, the thrust producing part in the middle.
So what does the SLS team expect to get out of this test?
Well, we're really looking to gain that confidence that our development tests gave us the data we expected to get. So we got a lot of data, 500 sensors at least. We're gonna review all of that and confirm that the booster does as we expect. So team's ready, I think. We're pretty excited, and we're looking forward to a good test today.
Excellent. Thanks very much, Bruce Tiller, NASA's Deputy Booster Program Manager for the SLS of the Marshall Space Flight Center. So while we proceed with the countdown, let's learn a little bit more about this new design.
Right.
This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern, and of course it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state-of-the-art. We've taken that avionics and actually tested in development units in a full flight configuration and are about to enter some qualification testing with that system. But in this particular test, we will actually control the thrust vector control system with the flight avionics.
The old shuttle program utilized a rubber insulation between the case segment and the propellant that contained asbestos, and so we selected a fiber called PBI, which is used widely in the fire protection industry. Developed a new rubber formulation and ended up with a rubber that is actually higher performing than the previous material, which allowed us to remove a fair amount of insulation and replace it with fuel and get a little bit more performance out of it. So not only is it environmentally friendly, it's a higher performing material and a higher performing rocket.
Structurally, we've had to make some changes. The aft attach point of this booster, in order to accommodate the structural configuration of the SLS vehicle, has been moved several feet aft. And actually, this QM-1 test will be the first test in a static configuration that we've done with that actual SLS attach point in place.
We had to design a new core and a new propellant grain inside the fuel that's inside the rocket. Part of that required us to design and manufacture all new tooling that forms the inside of the motor. We had to redesign our nozzle because we have a different performance, different things going on inside the motor, and so a large portion of the nozzle was redesigned.
Also, we've had a major effort over the last 2 years to try and improve the affordability of this vehicle, because the intent here was not only to have a higher performing vehicle, but to have one that actually costs less. And we believe we've achieved that, and this test of QM-1 will be evidence of that culmination.
As we've just heard, this 5-segment booster is improved in design and performance, but it is built using cases that have flown in space before. In fact, the aft skirt on today's booster flew on the first space shuttle mission with Bob Crippen and John Young, and also on the 7th space shuttle mission, launching America's first female astronaut, Sally Ride. And now these pieces that have powered such significant human space flights are playing a critical role in advancing our journey deeper into space and eventually to Mars. When qualified and completed, 2 5-segment boosters and 4 RS-25 engines will power SLS to space. For the last several hours, teams have been working to secure the test area and prepare for the final countdown. A little later, we'll listen in to the last several minutes as the test conductor and team make final preparations. But first, let's hear more from Bill and learn a little bit more about the boosters.
Thanks very much again, Stephanie. We're about 15 minutes away from this booster test, of course, outside of the 5-minute planned hold. And I am joined by the Chief Engineer for Booster Integration at Orbital ATK, Alicia Carrillo. Now, Alicia, first of all, tell everyone what booster integration means. What does that entail?
So booster integration is essentially the process of bringing together all of the components and making sure they're all assembled, checked out, and ready to go.
And of those many, what are the main components of the booster, though? We've heard about the aft skirt and the motor, of course.
Right, so we're essentially going from the nose cap down through the forward skirt into the motor elements, aft skirt, and then the exit cone.
So we're actually conditioning the motor today, and outside, for us anyway, it's a little bit overcast, a little bit chilly, not too bad though, but the motor's under almost tropical conditions.
It is. No, this motor has to be qualified from 40 degrees Fahrenheit up to 90 degrees Fahrenheit. This is our hot motor test, so it's just over 90 degrees. And you might think that 90 degrees doesn't sound hot, but keep in mind there's 1.5 million pounds of propellant up there that we had to get up to an average temperature of 90 degrees.
And this is the kind of temperatures that it could experience as it launches from Florida, right?
Essentially, long-term exposure in Florida.
Of course, that's not including the many, many degrees higher that it will be when it actually launches at the business end of the nozzle.
Right, quite a bit warmer on the inside and coming out the exit plane.
Well, I imagine that you and your team have been working very long, very hard on this. What goes into the months of preparation for this test?
You have a lot, going on to the physical assembly and integration, a lot of instrumentation going on, a lot of checkout, a lot of data systems, just making sure that everything is really queued up and ready to go.
So a lot of folks at the home at home may not know that you were actually the former test chief engineer out here at Orbital ATK, so you've had a lot of experience on this test stand. Can you tell us about, let's see, some of the safety that you and your team would take into consideration before you have a test like this?
So, obviously there's been quite a bit of safety elements going on so far. They cleared the bay, lots of gates and lights and clearing, everything going on right now. The closest people are in the control bunker, which is actually underground, and then we're here at the closest that people are allowed to be above ground.
Those that we're allowed to view it from here, of course. Now, we mentioned that the team has been here since 3 o'clock this morning when they first rolled back the building, because the booster itself is actually tied down, right? So it can't go anywhere.
Right. The booster is not going anywhere. It's it's into the thrust block, which is going to react the 3.6 million pounds of thrust. It's tied down in several locations through the test stand. It's got a restraint system, and the crew's just been busy making sure that everything is all tidied up.
Yeah, and I know they've been there. What are some of the other things that they've been doing to prepare the site for this test?
So, obviously smoke and fire coming out the back end. We've got some concrete blocks on and lots of sand on the back end. We want to protect that concrete as much as possible so we don't basically sandblast the whole aft end of the bay.
Also hit the side of that mountain right there. Now, we want to mention that we've also got quite a few of our NASA social media enthusiasts here with us today, have been using the hashtag SLS fired up and hashtag Journey to Mars. So you've taken some time to speak with them. You spoke with them this morning. What were some of the questions they were asking you?
They were really interested in, the procedures and the buy-off and what this qualification motor means to the overall verification. They're also pretty interested in, a female presence in engineering and in the aerospace industry.
Fantastic. Alicia Carrillo, the booster integration with Orbital ATK. Thanks so much for taking the time to talk with us today. So when it comes to, of course, igniting this booster, it's a bit more complicated than just lighting a match and running for the cover. We'll learn a little bit more about what it takes to light this proverbial candle with Gordy Russell, the Orbital ATK manager at the Marshall Space Flight Center.
So we are getting ready to static fire the QM-1 static test motor. It's a full rocket booster. It's made of 5 segments pieced together, and that's important as we've added another length of a segment into this booster to make it bigger and better. A lot of planning and work is done ahead of time as we design these rocket boosters to get the propellant geometry just right. We know at any given time during the burn of that motor what the thrust is and what the profile of the pressure is inside that motor. So with the new thrust profile for the SLS boosters, we've added an extra fin and changed some of the geometry of our propellant surfaces so we can burn more propellant at the beginning of the test, or beginning of the rocket firing. To get a solid rocket booster to burn, we have an igniter at the front end that is like a small rocket in itself, and it shoots a flame 150 feet down this entire rocket booster and ignites all the surface of the propellant all at once. Once you ignite a solid rocket booster, it can't stop it. You don't flip a switch to turn it on and off. At the same time, you can't turn a knob to increase your thrust or decrease your thrust. That's why it's important to design this beforehand, so we can get the amount of thrust we need at each point during this 2-minute burn to reach the maximum thrust at given time points that we need. At the beginning of the burn is when we have the most thrust, about 3.5 million pounds of thrust that we maintain for about 25 seconds. It takes just over 2 minutes of rocket firing for the propellant to completely burn out. And the propellant is burning really fast. It's got a certain rate that it's burning, but it's burning from inside out. So as every second goes by, it's like one layer of that propellant is essentially being peeled away and shot out the end of that rocket motor. And as this propellant burns and begins to create this mass that we are projecting out of this rocket, we are creating the thrust that we need to carry humans and astronauts and more weight into space.
We are at about T-minus 10 minutes and 40 seconds away from the actual test. As you see, the folks are gathering here in the viewing area. And the anticipation is palpable, one might say, as you take a closer look there at the motor. Up there in the test area, the booster, the entire full booster, I should say, tied down in the test complex area. I'm joined now by someone who has ridden a vehicle with 2 boosters similar to the design of today's test motor. Charlie Precourt, veteran astronaut, one-time chief of the astronaut corps, and now vice president and general manager of the propulsion systems with Orbital ATK. Sir, thanks very much for coming to join us today. First of all, you've got to be proud of your team making it to this milestone.
Immensely proud. This is a culmination of a lot of work, a lot of people working very closely with our NASA customer and the leadership of the NASA team. It's been a great effort, and we're really excited about what this booster can do.
So what will us here at the viewing area and, of course, the folks at home see today?
Well, we're going to ignite the booster and run it through a full series of tests that will verify the design that we put together here. In particular, folks will be able to see the nozzle fluctuating as we vector the thrust for the steerage that would be needed on a normal mission ascent to orbit. So,
well, let's talk a little bit about that. The steering mechanisms. It's just basically a couple of very small motors attached to the side, right?
Well, inside the aft skirt, we call it, near the nozzle, underneath the structure, there are 2 hydraulic actuators that move the nozzle left, right, and up, down, as we look at it on the stand up there today. And they can swing about 5 degrees in either direction, and that allows us to move that 3.5 million pounds of thrust just enough to steer the whole vehicle.
3.5 million pounds of thrust. That's a lot, and that's only for one booster.
That's right. That's right. One booster and multiply that by 2.
So you've had a little bit of experience on riding these. What can you tell us about that compared to this one?
Well, there's an immense amount of energy that we're controlling here, and I always describe it as if you take a chair at the dinner table and lay it over on the floor on its back, and you laying on the floor looking up, and imagine a giant hand reaching in under that chair and lurching you towards the ceiling. And then the push continues for 8.5 minutes, that same thrust in the back all the way to orbit. The key for a booster is to provide that thrust to be able to fly the vertical portion of the trajectory, lift all that weight to get us out of the atmosphere and turn the corner on our way to orbit.
And I think some of the things that folks are going to experience here anyway is you, of course, felt that all the way up, and we're going to feel it for a good 2 minutes here, whereas at launch, for the folks watching on the ground, it's really only for a few seconds.
That's right. At the launch site, you'll feel the vibration waving towards you, but once that wave is passed, the vehicle is out of sight, and you don't feel that anymore. You're going to feel it continuously here this morning.
We'll feel it, we'll definitely hear it, because I understand that with overcast skies, it directs all the acoustics, keeps it pretty close to the ground.
That's likely.
Charlie Precourt, thanks very much for taking the time to see it. Let's hear a little bit more about QM-1 and the SLS from one of Charlie's compatriots and fellow astronauts and a colleague here at Orbital ATK, Kent Rominger, and from the SLS program, Todd Bay.
This upcoming test, the QM-1 motor firing, is going to be a really big deal for us. These motors have 25% more energy than the motors we use to get the shuttle off the ground during the space shuttle days.
As a space shuttle astronaut, I flew the space shuttle 5 times. Every one of those was on the redesigned rocket motor that proved itself to be the most reliable rocket motor in the world. So this motor we're looking at here is called the qualification motor number 1. And it's actually the 4th motor in a series. We had 3 development motors. And on the development motors, they really are development, where you start out conservatively, you do a test firing, You see how well the insulators worked, how much thrust, what was the performance of the motor really, and then you start optimizing it.
So QM-1 is the first of 2 tests that will be used to qualify the motors for flight. We're actually already building the pieces of the second qualification motor flight. This is a really exciting time for all of us here. Coming off of Orion's first flight test in December, less than a month later we had the new RS-25 engines, which are the liquid engines that will power the rocket, have been tested at Stennis with a brand new state-of-the-art controller. The pieces of the rocket itself, the core, almost 30 feet in diameter, are all being manufactured at Michoud as we speak. There's a company called Conrad down in South Louisiana. They took our Pegasus barge, which is the barge we use to move the external tank around during the space shuttle days. They had to cut it in half and add 65 feet and stiffen it up to be able to handle the massive core that will come out of Michoud near New Orleans to be shipped down to KSC. And then in a few months, we'll actually complete the critical design review of the Space Launch System. This is where we actually say we are now done designing, and it's time to start putting all this hardware together and running it through its tests and verifying that it actually meets the requirements.
We're going to fly the SLS system in 2018, and between now and then, we're going to fire this motor. Less than a year from now, we'll fire the second qualification motor, and then we'll start assembling that Space Launch System rocket in Florida, launch in 2018. And the second flight of that rocket motor will take astronauts further into space than we've ever been.
From there, we're now into the proving ground, where we test the ability to be distant from Earth by days and weeks, and getting ready for the long-term exposure to deep space that gets us ready for a Mars mission in the future. So they say the journey of 1,000 miles begins with the first step. In this case, our journey is millions of miles away to Mars, and we're starting to take these steps. The next step is going to be this QM motor firing, and we're really getting excited to see it.
We're about 8 minutes away from today's booster test, which is scheduled for 9:30 a.m. Mountain Time. Everything is progressing normally in the countdown. We'll listen in now to some of the countdown, and you'll primarily hear the voices of the test conductor, Richard Rupp, and the test control coordinator, Howard Healy. This test is sometimes called a hot test because Orbital ATK has spent the last month getting all parts of the booster inside and out heated to a temperature of 90 degrees Fahrenheit. Combined with a second test next year at 40 degrees, teams will get a full range of data to feed into analytical models that inform how the booster performs at any temperature. More than 530 instruments are recording data during this test. In this test, the real heat will be inside the motor chamber, where the gas temperature reaches 5,600 degrees Fahrenheit, hot enough to boil steel.
T-minus 7 minutes.
Now verifying that the test range is clear of all personnel. Soon he will authorize the arming crew to surrender the fire control key to the test conductor. The arming crew is also verifying that the emergency diesel generator is online. The diesel generator acts as a backup power source in the unlikely event that the test area suffers a power failure during the static test.
T-minus 6 minutes.
Central Support Systems Operator, this is the test conductor. Turn on the water boost pump.
The boost pumps for the water deluge system have just been turned on. These pumps provide the necessary water pressure to feed about 1 million gallons of water through a series of nozzles underneath the motor chamber. It's essentially a bank of sprinkler heads that spray water up onto the chamber after the test to cool the case. The water deluge lasts a minimum of 20 minutes for the forward segments and at least 3 hours for the aft segment.
Roger. High-speed operator, monitor rock and tilt gas generator temperatures on the Genesis system and verify they are in tolerance.
Roger.
T-minus 5 minutes.
The test conductor is surrendering the fire control key to the test control coordinator. The key will be turned to the on position
test area
at T-minus 70 seconds when the final decision to commit the motor is made. In just a moment, the test conductor will poll all stations for a go for the test. Each station will report go before we proceed for ignition. Among the stations you'll hear make a call are the support systems, various data systems, and avionics.
T-minus 4 minutes.
This is the test conductor. Report system status.
The support systems are go for static test.
Low-speed data systems are go.
High-speed data systems are go.
Ultrasonic data system is go.
Avionics ballistic system is go.
Redline monitor system is go. Bus monitor system is go.
Motor temperatures are go for static test. Copy that. We are go for QM-1 static test.
And with that, all stations are go for today's static test of the SLS booster at 9:30 a.m. Mountain Time.
T-minus 3 minutes.
At the viewing area, all eyes are on the countdown, now less than 3 minutes away from the firing.
T-minus 145 seconds. High-speed operators begin recording.
All high-speed data systems are recording.
Roger. T-minus 2 minutes. Low-speed data operators begin recording.
All low-speed data systems are recording.
Roger. Bus monitor operators select stop all followed by start all to begin a new recording file.
Bus monitor is recording a new file.
Roger.
Ultrasonic system is recording.
Roger. T-minus 90 seconds. T-minus 80 seconds.
Test control coordinator, stand by to commit the motor.
Standing by. T-minus 70 seconds.
Commit the motor.
Motor is committed. T-minus 60 seconds.
1 minute to ignition. The test is a go.
T-minus 50 seconds. T-minus 40 seconds.
Pad flush is on.
T-minus 30 seconds. Minus 25. Minus 20. Minus 15. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire.
We have ignition of NASA's Space Launch System 5-segment solid rocket booster.
Plus 10. Plus 20. Plus 30. Plus 40. Plus 50. T plus 60 seconds. Plus 70. Plus 80.
Central Support Systems Operator, enable the deluge, CO2, and quench tool controls.
Controls are enabled.
Plus 90.
Open the accumulator enable valve.
Accumulator enabled.
Plus 100. Plus 105.
Activate aft deluge.
Aft deluge activated.
Plus 110.
Activate forward deluge.
Forward deluge activated.
T plus 120.
Activate head end CO2.
CO2 activated.
Activate quench tool command forward and aft CO2.
Activated.
T plus 165 seconds. High-speed data operator stop recording.
The full 2-minute test has concluded.
High-speed recording
Now
is
the
complete.
carbon dioxide
Roger.
quench
High-speed
arm pumps
operator
31 tons of CO2 into the booster. The carbon dioxide quenches any burning of the insulation without damaging it to preserve the state it was in during the test. This allows the team to get the best data about how it will perform in flight. There's quite a bit of action remaining for the teams here as they ensure the test area is safe and the data are recorded. Following motor burnout, the chamber will be sprayed with 2,300 gallons of water per minute on the underside of the case to help cool it down. This will cool the chamber from 1,000 degrees Fahrenheit to 300 degrees Fahrenheit.
Avionics engineer, verify that the Solistic has finished saving the log files.
In work.
Roger. Redline monitor operator, transfer the log file to the local computer.
Roger, in work.
Roger. Bus monitor operator, transfer the data files to the local computer.
In work.
T plus 4 minutes.
Redline monitor files have been transferred to the computer.
Roger.
Let's go back out to Bill, where he's standing by for first reactions from those who were outside watching the test.
Thanks very much, Stephanie. Yeah, 2 minutes of excitement and exhilaration, followed by jubilation from the crowd, as well as some of the gentlemen who helped make this happen. I'm joined by Alex Priscos. He's the SLS booster manager at the Marshall Space Flight Center, and of course, rejoined by Orbital ATK's Charlie Precourt. Charlie, let me start with you. Everything seemed to go well, and how do you think it looked?
It looked really clean. We're very excited. It's a great result. You could feel the pressure coming off the motor. You could see the plume and watch the vectoring. It all looked great. We'll be looking for the quick look data, but really nice result.
I think what was exciting, and I haven't been to one of these in a couple of years, so it was really exciting to see is you've got that initial pause when everything loads, you see all the smoke and the fire, and then suddenly that sound wave hits you.
Great little science demonstration for the speed of light, the speed of sound, you know, the little delay, and then the noise hits you. Really pretty neat.
I know that you and your crew are far from finished. What do you immediately is your crew doing up there right now?
So we're making sure all the systems are shut down. You know, we had hydraulic power units running and so forth. All of that post-fire stuff begins. We got quenching going on. There's a lot of water systems up there cooling the belly of the booster because a lot of the residual materials in there that are so hot, that plume was 5,000 degrees. A lot of that hot stuff is laying in the belly of the booster, so we got cooling water jets cooling off the belly of the booster so that it doesn't get too hot. And then over time, we'll be able to go up and take a look, and the dissection will begin, and all the data will start to flow, and we'll be looking for qualification.
And if I'm not mistaken, a lot of that hardware can be reused, right?
Absolutely. All of this stuff will get recycled and used in either another test or maybe in flight.
Thanks very much, Charlie. Let me turn now to Alex Priscos, once again with the SLS program out of the Marshall Space Flight Center. You look like a happy man.
I am very happy this morning. Great test. Just a fantastic result. You used a stopwatch. We haven't seen the real preliminary data, but we get a little bit with just a watch, and this thing was about as perfect and nominal as it could be. We were looking for a 2-minute firing time, and that's what we got. So it's great. I'd like to thank Orbital ATK and the NASA team for all they've done to get us here. It's been just a fantastic effort on everybody's part.
So let me ask you, I know you've got a lot of your team here as well as you met some of the folks from Orbital ATK as well as some of our NASA social media visitors. What has been some of the reaction from some of them about being here and then seeing something like that? I saw lots of handshaking on your way up here.
You know, the enthusiasm that you get in a test like this is just incredible. It shows what these kind of tests mean to everybody that literally spend years and years and hours and hours and hours every week working on it, as well as those that just show an extreme amount of interest. And to watch the momentum and the interest build in this program has absolutely been fantastic, and it has really, really built consistently the last several months.
So what's next for the booster team in the short term?
So in the short term, we'll look at this data. We'll look at it on several levels. We'll get our first pre-look at the data in probably about an hour, but we'll continue to dissect and go deeper and deeper into data for several months. Meanwhile, we will be preparing qualification motor number 2, which is our second qual test, which will be a cold test to understand the performance in a cold condition. And that will probably happen early next year.
So what are some of the finer points of the data that you're going to be looking for?
Pressure time curve, which really gives us a sense of power and when it happens and how much. We'll be looking at the erosion of the insulator, which tells us how much margin we have thermally in the system. And we'll be looking at nozzle erosion. Those are just 3. There's several hundred parameters, but those are the 3 that we'll be looking at very, very hard and very quickly.
All right, excellent. Well, thanks once again very much to the both of you. Congratulations on a successful test, and I know a lot of us, I speak for many of us out here who are just glad we could have been here to be a part of it. Once again, Charlie Precourt with Orbital ATK, Alex Priscos from the SLS booster program. So, gentlemen, we're going to take, before we head back inside to Stephanie for a few last words, let's take a look at some of the replays of the test we just saw.
We have ignition of NASA's Space Launch System 5-segment solid rocket booster.
Onboard systems operator, enable the deluge, CO2, and quench tool controls.
Controls are enabled.
Plus 90.
Open the accumulator enable valve.
Accumulator enabled.
Plus 100.
Fire.
We have ignition of NASA's Space Launch System 5-segment solid rocket booster.
Plus 10. Plus 20. Plus 30.
We have ignition of NASA's Space Launch System 5-segment solid rocket booster.
Bus 10. Plus 20. Plus 30. Plus 40. Plus 50. T plus 60 seconds. Plus 70. Plus 80.
Central Support Systems Operator, enable the deluge, CO2, and quench tool controls.
Controls are enabled. Plus 90.
Open the accumulator enable valve.
Accumulator enabled. Plus 100.
Today's successful test of the Space Launch System 5-segment booster is a major milestone on our journey back into deep space and onto Mars. But today's a busy day for other parts of NASA as well. We have the Earth Science mission and the International Space Station program have major events happening today. At 11 a.m. Mountain Time, 1 p.m. Eastern, join us for the science briefing for NASA's magnetospheric multi-scale mission, which launches Thursday at 10:44 p.m. Eastern. Today at 1 p.m. Mountain Time, 3 p.m. Eastern, NASA TV will air live coverage of the undocking of 3 International Space Station Expedition 42 crew members, including NASA astronaut Barry Wilmore, as they begin their journey home after 167 days in space. Thank you for joining us for today's live coverage of the SLS booster test from Orbital ATK's test complex at Promontory, Utah. I've been your host, Stephanie Shearholtz. We'll conclude today's broadcast with a note that you can follow us and keep up to date on all